Hey guys, tonight we drop you onto the most hostile desert on Earth, though your brain rebels at the word desert when all you can see is ice as far as your eyes can stretch. It is January, the year 1959, and you are standing at a Soviet outpost in East Antarctica. The thermometer laughs in red mercury at 60 Goji, and the air is so sharp it feels like it slices your lungs with every breath. The snow squeals under your boots like brittle styrofoam, and the silence is so total that even your heartbeat sounds like a drum. Somewhere behind you, men in thick fur parkas shout over the grinding roar of a tracked vehicle. They're not out here for fun. They suspect something incredible lies beneath this frozen crust, but they don't yet know how deep. You can taste diesel fumes on your tongue and a hint of metal from the cold air clawing at your teeth. You're standing on top of an empire of ice, 4 kilometers thick. Beneath your feet, hidden away in permanent darkness, water may be sloshing in vast liquid chambers that have not seen the sun in millions of years. And here's the blunt truth: you probably wouldn't survive 5 minutes if dropped outside camp without gear, so maybe tuck those hands into your mittens. If you love slipping into history's strangest, coldest mysteries, don't forget to like, subscribe and ring the bell for more. Drop your location and local time in the comments. It's always wild seeing who's tuning in from warm beaches while we freeze down here in Antarctica. And tonight, when the ice whispers its secrets, remember, even Earth keeps parts of itself hidden from us. Now you trudge forward, boots sinking with a crunch into snow older than your civilization. Your breath fogs the air as you look across the plateau, an endless white sheet that hides far more than it reveals. The first explorers who came here, Scott, Amundsen, Shackleton, barely survived on the surface, but what really lurked below was not yet imagined. Early suspicions started when planes flew overhead in the mid-20th century, dragging radar instruments that could see through ice. The echoes they bounced back told a strange story. The base of Antarctica was not all rock. In certain spots, the signal behaved as if it had struck liquid water. The idea sounded absurd: liquid water under that much ice, in a land where air temperatures almost never rise above freezing. Scientists argued. Some claimed the radar was faulty, others pointed to the sheer pressure of the overlying ice, 4 kilometers thick, meant that even at below zero temperatures, water could remain liquid. The base of the ice sheet was also insulated by geothermal heat, slowly seeping upward from Earth's crust. Together, pressure and heat created conditions where lakes could exist, trapped, isolated and completely unknown. By the 1960s, expeditions were already hinting that Antarctica wasn't just a frozen block. Tracks in ice flow patterns suggested rivers and drainage systems moving invisibly below. It was like discovering plumbing in a house you thought was solid concrete. You stand there, feeling how your weight presses into snow that might sit above a body of liquid as large as Lake Ontario. A chilling thought, though, let's be honest. Everything here is chilling. Scientists began to argue passionately. Could these lakes exist for millions of years, sealed away, untouched by modern air? If so, they might hold life. Microbes locked in time, evolving along their own lonely branch, since before humans learned to sharpen stones. You imagine that right now, thousands of meters beneath you, microbes might drift in black water, unaware of your existence, unaware of the Cold War drilling machines parked above them. It was just suspicion then, but suspicion is how great discoveries are born. The ice gave hints through seismic thuds, radar echoes, and the way glaciers slipped faster in some regions than in others. Where they slid quickly, lubrication was suspected, water beneath, greasing the flow. By the 1970s, scientists could no longer shrug it off. Subglacial lakes were likely real. The only question left: how many, and how enormous? The white horizon glitters in front of you, empty and endless, but you now know it's an illusion. Antarctica is not a blank, it is riddled with secrets, and every gust of katabatic wind across your hood reminds you that you're standing atop a treasure chest of hidden water waiting to be unlocked. The ground beneath your boots might not just be ice, it might be a ceiling, and below it an entire alien world. You shuffle forward across the ice, your breath a frosty plume in the air, and picture yourself in the shoes of those first scientists who began to piece this mystery together. The mid-20th century wasn't exactly the age of high-tech satellites and fancy drones. Most of the time, research in Antarctica meant dragging heavy equipment across crevasse-ridden plains, setting up temperamental instruments in winds that could tear metal poles from the ground, and hoping the batteries didn't die from the cold before you got a single usable reading. Still, a few pioneers pushed technology to its limits and began listening to the ice itself. One of the first tools was seismic sounding. The method was brutally simple. set off a small explosive at the surface, then measure how long the shockwaves took to bounce back from the layers below. It was like banging on the ceiling of a basement and waiting for the echo to tell you how big the space beneath might be. By the 1950s and 60s, seismic teams noticed something odd. Instead of a jagged, rough reflection that you'd expect from solid rock, some areas returned signals as smooth as glass. That smoothness hinted at liquid water, a flat surface hidden under unimaginable pressure. At first, this idea met skepticism. After all, Antarctica was thought to be locked down by a grip of ice, a place of stillness. Water was supposed to freeze, not flow, but radar began to back up the story. Ice-penetrating radar, developed during World War II for military purposes, was repurposed by geophysicists. When planes flew over parts of East Antarctica dragging radar equipment, the echoes suggested interfaces, not between ice and rock, but between ice and something else, something that behaved electrically like water. By the mid-1960s, these hints had piled up into a whisper that scientists could no longer ignore. Could Antarctica harbor a system of buried lakes, hidden under kilometers of ice? The evidence wasn't just in the radar. Glaciologists studying the movement of ice noticed certain areas slid far faster than expected. It was as though they were lubricated from below, as though rivers, yes, rivers, were coursing through the darkness under the ice sheet, feeding and draining lakes. The concept was radical, because it rewrote the way people thought of Antarctica. The common picture was a silent continent, frozen solid, locked for eternity. But this new theory suggested something dynamic. Beneath the hard, blindingly white surface lay a world in motion, water pooling, shifting, draining, filling, and emptying in cycles we couldn't yet see. Imagine the difficulty of convincing your peers. You're standing in a conference hall in the 1970s, showing blurry radar traces with weird wobbles, arguing that it means there's a lake the size of a small country under the ice. Your colleagues raise eyebrows, some laugh quietly, others shake their heads. You're basically telling them that Antarctica has indoor plumbing, and no one has ever glimpsed a pipe. But slowly, piece by piece, the data grew too consistent to dismiss. Seismic thumps, radar blips, satellite tracking of ice flow, all told the same story. Something was hiding beneath. Something that defied the frozen stereotype. And here's the kicker. Scientists realized this hidden water wasn't just a curiosity. If true, it meant Antarctica might have been hiding life, entire microbial ecosystems that had not been exposed to the outside world for millions of years. They would have evolved in the dark, sealed beneath ice, living on chemical traces leaching from bedrock. To find such life would be like peering into Earth's own time capsule, what microbes were doing back before humans even existed. By the time the Cold War heated up in the late 20th century, both Soviet and Western scientists were eyeing the Antarctic plateau with renewed fascination. Somewhere down there, beneath the silence and the storms, entire lakes might be waiting. The trick now wasn't convincing themselves of the possibility, it was proving it to the world. You stand on the windswept surface, squinting into the glare, knowing that the first concrete evidence of a massive subglacial lake was about to emerge. The suspicion would soon harden into discovery, and the name Vostok would enter history. You pull your hood tighter against the stinging wind as the scene shifts in your mind to the Soviet Union's Vostok station, one of the most isolated research outposts on the planet. It sits smack in the middle of East Antarctica, far from the relatively busy coastal bases. Founded in 1957 during the International Geophysical Year, Vostok quickly became a symbol of Cold War grit. Tiny clusters of prefab huts and labs buried in snowdrifts, powered by diesel generators that roared against the silence, staffed by crews who could go months without seeing another human outside their team. At the time, the Soviets weren't drilling for water, they were drilling for climate records, coring through ancient ice to capture bubbles of atmosphere trapped for hundreds of thousands of years. Every meter of ice pulled up was a frozen diary entry of Earth's past weather. By the 1970s, Soviet glaciologists had sunk boreholes more than 2 kilometers down, hauling up cylinders of crystal-clear ice that crackled like old glass. But here's where things got weird. The ice cores showed sudden changes in chemistry, as if the bottom layers weren't just frozen snow but had refrozen from liquid. That meant the drill had passed through an ancient interface, a place where the ice above had met liquid water below. It was as if the drill was knocking on the ceiling of an enormous hidden chamber. The evidence grew overwhelming. Radar surveys run by British and Soviet teams in the 1970s and 1980s showed a reflection beneath Vostok Station so large and smooth, it could only be explained by a liquid surface, not a pond, not a little puddle, but a lake stretching over 50 kilometers long and 50 kilometers wide, sealed beneath 4 kilometers of ice. In fact, it rivaled Lake Ontario in volume. That's right, a freshwater body, the size of a great lake, was hiding under a continent no one ever thought could host liquid water. Lake Vostok, as it came to be known, instantly became a scientific obsession. Its isolation was mind-bending. The lake's surface had not seen daylight for at least 15 million years, maybe longer. Its waters were pressurized by the crushing ice above, heated slightly from Earth's crust below, and completely shielded from contamination by the surface world. It was the closest thing on Earth to a completely alien biosphere. By the 1990s, international attention surged, the Cold War was winding down, and collaboration was suddenly possible. NASA looked at Vostok and saw Europa, Jupiter's icy moon thought to harbor a subsurface ocean. Biologists looked at Vostok and saw a time capsule of microbial life. Climatologists saw sediment records at its bottom that could reveal Antarctica's hidden past. Every field of science wanted a piece of it. But drilling into a lake like that wasn't as easy as dropping a straw into a soda. The ice cap above Vostok was 4,000 meters thick. The temperatures down there hovered around 3 degrees C, yet the pressure kept the water liquid. If a drill broke through too quickly, the pressurized water could shoot upward violently, contaminating the pristine ecosystem, or worse, destroying it. Engineers argued endlessly about methods. Should they use hot water drills, mechanical drills, or clean chemical fluids? Every option risked bringing in microbes or chemicals that would ruin the untouched environment. The Russians pressed on. Through the 1990s and into the 2000s they drilled carefully, using kerosene and freon to keep the borehole from freezing shut. By 2012, after decades of effort, they finally reached the lake. When the drill broke through, lake water surged upward into the borehole and froze, leaving a plug of pristine ice. Later analysis of this refrozen sample revealed signs of microbial DNA, life clinging on in one of the most hostile places on Earth. You stand in your mind at Vostok Station, the endless plateau stretching in all directions, diesel smoke curling into a pale sky. Under your boots lies a hidden ocean larger than some countries. It's silent, ancient, and sealed, but no longer a secret. What started as faint radar echoes had now transformed into one of the greatest discoveries in polar science, and Vostok was just the beginning. The wind howls across the white expanse as you picture yourself in the cockpit of a survey plane in the 1990s. It's not some sleek jet, it's a modified Twin Otter or a lumbering LC-30 rigged with gear that looks like a Frankenstein's mix of science fair and Cold War espionage. Strapped to the belly and wings are instruments that can see through ice-penetrating radar antennas, gravimeters, magnetometers, and laser altimeters. The flight crew sits bundled in heavy parkas, condensation frosting on the windows, as the plane hums steadily over featureless terrain. Below, the Antarctic plateau stretches without end, but the machines are revealing something very different. Those radar pulses, like invisible flashlights, slice through the kilometers of ice, bounce off whatever lies beneath, and return faint signals. At first glance, they're squiggly lines scrolling across green cathode ray screens. But in those squiggles lies a revelation. Antarctica isn't solid. Beneath the ice sheet, water gleams in the radar's eye. Smooth, flat reflections mean liquid surfaces, and there are not just one or two, there are hundreds. As data piles up, scientists begin to map the hidden hydrology of the continent. By the late 1990s, over 140 subglacial lakes have been identified, many clustered near East Antarctica's highlands. Some are small, a few kilometers across, others are giants, rivaling Vostok in sheer scale. Over the following decades, the number balloons. Today we know of more than 400, scattered beneath the ice like dark jewels embedded in frozen stone. And the lakes aren't isolated. That's the shocking part. Satellite altimetry, precise measurements of the ice surface height from space, shows the surface rising and falling mysteriously over months and years. That heaving motion corresponds to lakes filling and draining below. One lake empties, another swells. Some discharge into hidden rivers that snake hundreds of kilometers, feeding still more lakes before dumping into the Southern Ocean. The whole system behaves like a living organism, pumping, shifting, responding to the weight and flow of the ice above. Imagine standing on what looks like a featureless sheet of ice, knowing that beneath you an entire plumbing system is at work. A pulse of water might be moving unseen below your boots, sluicing down a buried channel toward the coast. It's like living above an invisible tide, one that rises and falls without warning, in darkness eternal. Geophysicists realize this subglacial water network is not just a curiosity, it plays a crucial role in how Antarctica's ice sheet behaves. Where lakes and rivers lubricate the base, ice flows faster, like a glacier on roller skates. Where the water freezes, ice grinds to a halt, locking up vast regions. In other words, these hidden lakes aren't passive, they control how much ice eventually slides into the sea, and therefore how much global sea level rises. This insight changed everything. For climate science, Antarctica went from a frozen wasteland to a complex system with moving parts, plumbing, and feedback loops. It also meant that studying these lakes wasn't just about curiosity, it was about understanding the future of Earth's coasts. And for biologists, the potential was mind-bending. Dozens, maybe hundreds of unique lakes, each sealed off for millions of years, each with its own chemistry, pressure, and nutrients. Each one could harbor microbial ecosystems, as alien to us as life on another planet. You imagine the map of Antarctica now, not as a white void, but as a secret atlas, lakes connected like beads on buried strings, rivers glowing faintly beneath 4 kilometers of ice. What once seemed lifeless has been revealed as dynamic, restless and full of hidden worlds. And somewhere among these hundreds of lakes, a few were about to offer the first real taste of what lived and thrived beneath the ice. You shift your weight on the ice, and if you could peel away the frozen crust, like lifting a floorboard, you'd see something that looks oddly familiar: rivers, streams, and lakes, but all hidden in the dark. Antarctica's subglacial water system isn't a random scatter of puddles, it's a network, a kind of underground plumbing that keeps the entire ice sheet moving. Here's how it works. Snow falls on Antarctica year after year, piling up into layers that compress into ice over hundreds of thousands of years. That ice thickens until, in places, it's more than 4 kilometers deep. The sheer weight presses down on the base, and at those crushing pressures, the melting point of water drops below zero. Add a touch of geothermal heat from the Earth's crust, plus the friction of ice slowly grinding across rock, and voila, water forms at the bottom. But it doesn't just sit there, it collects into basins, flows through valleys, and connects lakes like beads on invisible strings. Some of the water cycles slowly trapped for centuries, other parts rush through channels, filling one lake until it overflows and drains into another, sometimes in sudden surges that move billions of liters in weeks. Scientists have tracked these pulses using satellite altimetry, watching the ice surface above bulge upward as a lake fills, then sink again as it drains. It's like watching a lung inhale and exhale, only the lung is the size of a mountain range, and the breath takes months. One of the strangest aspects is how this plumbing system affects the ice sheet above it. Where water flows freely, the ice slides faster, greased like a puck on an air hockey table. Where the water freezes back into the base, friction locks the ice down. This push and pull determines whether glaciers creep slowly to the sea or surge forward in sudden bursts. A single hidden flood can destabilize kilometers of ice shelf, which in turn nudges sea levels upward across the planet. So yes, while you sip your latte thousands of kilometers away, your coastal city might indirectly be at the mercy of a hidden gush of subglacial water beneath Antarctica. But the lakes aren't just mechanics of ice flow, they're laboratories of the bizarre. Imagine a lake cut off from the surface for 15 million years, sealed by kilometers of ice, never touched by sunlight. The only inputs are tiny trickles of meltwater and minerals leaching from bedrock. These conditions are so extreme that scientists call them analogues for extraterrestrial oceans, like the buried seas of Europa or Enceladus. If life can adapt here, it makes the case stronger that microbes could thrive under the icy crusts of moons orbiting far-off planets. Geologists point out another prize. Sediments on the bottom of these lakes are treasure chests of history. Each layer might hold pollen, volcanic ash, or chemical traces from warmer periods in Antarctica's past, when forests once grew where glaciers now stand. Drill carefully enough, and you don't just find water, you find pages of Earth's climate diary, sealed in mud. You glance around the endless white and realize that beneath every bootstep, something is shifting, pulsing, or waiting. The ice may look still, but in reality it's being nudged and tugged by an invisible plumbing system that links the heart of Antarctica to the edges of the ocean. It's not just frozen wasteland, it's dynamic, it's alive in its own icy way, and it's quietly rewriting how we understand the planet. And while scientists began mapping the hydraulics of this underworld, another question pressed forward: if these lakes are so isolated, so dark and so ancient, could anything possibly be alive inside them? You pull your mittens tighter, because even imagining what comes next makes the cold feel sharper. Beneath that crushing weight of ice, in total darkness, in water colder than your freezer, but still liquid, life exists. And not just the kind of life you scrape off a dirty kitchen sponge. These are microbial survivors that have managed to adapt to an environment most biologists once considered impossible. When scientists finally managed to collect refrozen samples from Lake Vostok's borehole, the big question was, did anything live down there? The first reports were controversial. Tiny traces of microbial DNA showed up, but skeptics wondered if they were just contamination from the drill fluids. After all, kerosene and antifreeze weren't exactly clean, yet as methods improved and other lakes were probed, the story became clearer. Yes, there are microbes, and yes, they belong down there. Think about it. These organisms thrive in total absence of sunlight, which means photosynthesis is out of the question. Instead, they rely on chemosynthesis, scraping energy from the tiniest chemical reactions, oxidizing iron, sulfur, or even the trace minerals dissolved in the pressurized water. It's survival stripped down to bare chemistry. Imagine a life where your entire food chain is nothing but rock dust and faint whispers of gases trickling through the ice. Glamorous? No. Effective? Absolutely. In Lake Whillans, when American teams finally sampled it in 2013, they found living bacteria and archaea that weren't just hanging on but forming entire communities. Some broke down organic carbon buried in sediments, others cycled nitrogen and sulfur, and still others lived off hydrogen produced when rocks were crushed under shifting ice. It's a whole food web, one that doesn't care about the sun in the sky. To wrap your brain around this, imagine you're a microbe, drifting in the ink-black waters of Whillans. Pressure squeezes you with a force hundreds of times greater than at sea level. Temperatures hover just below freezing, cold enough to slow most chemical reactions to a crawl. Yet you tick along, breaking apart molecules, sharing nutrients in a microscopic economy that has kept your lineage alive for maybe 1,000,000 years. If microbes could roll their eyes, they'd probably laugh at humans who call Antarctica inhospitable. For them, it's home sweet home. And here's the kicker: some of these microbes may have been isolated since long before humans even thought of inventing writing, agriculture, or ticked. Studying their DNA is like looking at evolutionary time capsules, versions of life that branched off and went their own way in a locked vault of ice. Each lake may host different lineages, because each has been sealed on its own timeline. That makes Antarctica not just one alien world, but hundreds of them, each with its own microbial civilization. Biologists are giddy because this also strengthens the case for life elsewhere. If microbes can thrive here, sealed under kilometers of ice, then why not on Europa with its buried ocean beneath a crust of ice, heated by Jupiter's tides? Why not on Enceladus, where geysers spit water vapor into space from a hidden sea? By poking into Antarctic lakes, scientists are essentially rehearsing for astrobiology field trips to other planets. Standing above the ice, you almost feel like an intruder. Down there, entire ecosystems tick away in silence, indifferent to whether we ever discover them. To them, our drilling rigs, our satellites, and our debates are just background noise, if they even had ears to hear. For millions of years they've survived without sunlight, without oxygen, without contact, and the irony is we call them extremophiles, when really, they're perfectly at home. It's us who wouldn't last 5 minutes without a parka and a heater. These subglacial lakes aren't just hiding water. They're hiding answers to one of the biggest questions humans can ask: what counts as a habitable world? And every drop of lake water that comes back with signs of life whispers the same thing: life is tougher, stranger, and more stubborn than we ever gave it credit for. Your boots crunch against the brittle crust as you look out over the white desert, but in your mind, the horizon suddenly tilts outward, past the edge of Earth itself. Because here's the wild thing: Antarctica's buried lakes aren't just Earth science. They're rehearsal stages for alien worlds. Take Europa, Jupiter's ice-coated moon. Telescopes and spacecraft tell us its outer shell is a solid crust of frozen water, maybe 10 to 20 kilometers thick. Beneath that, a global ocean, salty, dark, and warmed by the moon's flexing under Jupiter's gravity. Sound familiar? Replace Antarctica's kilometers of ice with Europa's, swap geothermal heat for tidal heating, and you've basically got the same concept: liquid water sealed off under ice, cut off from sunlight, possibly for billions of years. Now jump to Saturn's moon Enceladus. That one doesn't even try to hide. Its south pole shoots plumes of water vapor and ice crystals straight into space, like a cosmic soda can that someone shook a little too hard. Scientists suspect those geysers come from another buried ocean, laced with salts and organic molecules. NASA's Cassini spacecraft even flew through the spray and detected compounds that look suspiciously like the building blocks of life. And here's where Antarctica comes in. If life can exist under kilometers of Antarctic ice, scraping by on chemical energy alone, then suddenly the idea of microbes swimming in Europa's ocean, or clinging to rocks under Enceladus's crust, doesn't sound like sci-fi, it sounds plausible. Antarctica becomes a training ground, the closest alien laboratory we've got without leaving Earth. That's why astrobiologists perk up every time a new Antarctic lake is sampled. Finding microbes that metabolize sulfur or iron in Willans. Great, Europa's ocean floor is probably littered with sulfur-rich rocks. Discovering bacteria that tolerate crushing pressure. Perfect, Europa's ocean could be 100 kilometers deep. Finding communities that thrive without oxygen or sunlight. Exactly what you'd expect under Enceladus's ice. The parallels are almost eerie. When you hold a vial of cloudy Antarctic lake water, you're not just holding a piece of Earth, you're holding a mirror to space. What happens in those sealed lakes might be the same playbook life follows in distant oceans we can't yet reach. Of course, there's a cheeky reality check. No one's about to send a scuba diver down into Lake Vostok or pack microbes in a cooler and FedEx them to NASA. The logistics alone are brutal, but the concept fuels billion-dollar missions. Europa Clipper, launching soon, is literally designed to scan that icy moon the way radar planes scanned Antarctica. Subsurface oceans, possible geysers, chemical fingerprints, all of it echoes research born in this frozen desert you're trudging across right now. So as you pull your parka hood tighter against the Antarctic wind, you realize you're standing on Earth's most convincing preview of alien oceans, and the question that once felt far away, are we alone, suddenly feels less cosmic and more local. If microbes can thrive in Antarctica's subglacial lakes, then maybe the galaxy is more crowded than we think. And just as the comparisons were getting thrilling, another problem loomed. If you want to drill into these hidden lakes to prove life exists, how do you do it without wrecking the very ecosystems you're trying to study? The wind rattles against your hood, and you can almost hear the hum of generators in the distance, because this part of the story isn't about discovery, it's about engineering. It's one thing to know subglacial lakes exist, it's another thing entirely to actually get inside them without turning the whole thing into a giant accident. Here's the challenge, you're trying to drill through up to 4 kilometers of ice, in one of the coldest places on Earth, without contaminating what might be a pristine ecosystem sealed for millions of years. Imagine drilling into a vault that's been locked since the Miocene, and your first move is to spill kerosene all over the floor. Yeah, scientists lose sleep over that. The Russians at Vostok Station learned this the hard way. Their borehole used a cocktail of kerosene and freon to keep it open, preventing the ice from squeezing shut. In 2012, after decades of painstaking effort, they finally broke into Lake Vostok. The good news, they reached it. The bad news, when lake water surged upward into the borehole, it instantly froze on contact with the cold air, trapping a plug of ice. Samples taken later contained microbial DNA, but skeptics immediately asked, was that life from the lake, or just microbes introduced by the drilling fluids? It was a win, but a messy one. The British faced their own drama at Lake Ellsworth in 2012. They had designed a high-tech hot water drill to melt down nearly 3 kilometers of ice, planning to pump out clean samples, but Antarctica is a place where plans go to die. The drill hit technical issues, pressure valves failed, and the borehole collapsed before they ever reached the lake. Millions of pounds sterling, years of preparation and no water to show for it. Meanwhile, the Americans were quietly refining their methods. At Lake Willans, in 2013, the Willans Ice Stream Subglacial Access Research Drilling Wizard project used a clean hot water drill sterilized with UV light and filtration. They also worked shallower. Willans sits only about 800 meters below the surface, practically a puddle compared to Vostok. The payoff? Success. They reached the lake, pulled up water and sediment samples, and actually found living microbes, the first uncontested proof of life in a subglacial lake. So why all the fuss about contamination? Imagine a pristine lake that's been sealed for millions of years. Its microbial communities have balanced themselves on a knife's edge, surviving in nutrient-starved conditions. Drop in a single foreign bacterium, something common on human skin for example, and it could outcompete the locals. throwing off the ecosystem forever. To scientists, that's not just bad lab practice, it's scientific vandalism. Worse, if these lakes are analogues for extraterrestrial oceans, contaminating them now would be like contaminating Europa before we ever even get there. The race to drill cleanly is a mixture of science, politics, and a bit of ego. Russians, Americans, and Brits each wanted to be first, but the lakes are patient. They've been sealed for millions of years and they aren't going anywhere. The real prize isn't speed, it's precision. And so, each attempt became part of a bigger learning curve: how to drill cleaner, how to keep boreholes from freezing, how to sterilize kilometers of tubing, and how to prove that what you pull up truly belongs to the lake, not your drill. It's a logistical nightmare, but every success, even the small ones, moves us closer to exploring these hidden worlds properly. Standing on the ice, you realize the story of Antarctica's lakes isn't just science, it's an engineering saga. The lakes keep their secrets well guarded, and only those willing to battle the cold, the ice, and the risk of contamination can even try to ask questions. But when the questions get answered, the results are extraordinary. And one of those extraordinary answers came from the first successful clean drilling project at Lake Whillans, a revelation that proved these lakes weren't lifeless at all. The generators hum, the hot water hoses hiss, and you can picture yourself standing in January 2013 at a temporary camp on the Whillans ice stream. This isn't the desolate high plateau of Vostok, it's West Antarctica, closer to the coast, where the ice is thinner but far more restless. The project is Wissedard, and the goal is bold: reach Whillans Subglacial Lake, a body of water sealed beneath 800 meters of ice, without contaminating it. The setup looks like an industrial nightmare. A cluster of shipping containers bristle with pumps, heaters, and filters, a tangle of hoses, snakes across the snow, spraying steam into the air. Scientists in red parkas scurry between stations, monitoring gauges and sterilizing equipment. The entire system runs on clean hot water, melted snow, filtered, UV sterilized, and blasted down through the ice to bore a shaft wide enough to lower instruments. No kerosene, no antifreeze, no dirty fluids. Just water. It's like trying to tunnel with a fire hose, only at Subglacial, where your tunnel walls try to refreeze as fast as you melt them. It takes days, but eventually the borehole punches through, instruments slide down into the darkness, and pumps begin drawing water to the surface. For the first time, scientists hold liquid from a subglacial lake that hasn't seen daylight in millennia. The analysis is staggering. Under the microscope, the water isn't sterile, it's alive. They find bacteria and archaea adapted to pressures and temperatures that would kill most organisms instantly. Some of these microbes feed on ammonia and methane, others on iron and sulfur. In the sediments at the bottom, more communities appear, recycling ancient carbon and energy sources that have been trapped since before humans built cities. Far from being barren, Whillans is bustling on a microbial scale. And there's more. The sediments tell a story of movement. The lake has filled and drained repeatedly, flushing water through hidden channels that connect to the Ross Sea. Tiny fossils in the mud show that at some point in the distant past, seawater intruded beneath the ice sheet. That means this sealed lake has exchanged materials with the ocean, linking Antarctica's hidden plumbing to global systems. For climate scientists, this is gold. It means subglacial lakes aren't closed jars. They're dynamic, shifting parts of Earth's hydrological cycle. They move water, nutrients, and even carbon between the ice sheet and the ocean. That process affects how fast glaciers flow and how stable the ice shelves are at the coast. A surge of water from lakes like Whillans could weaken ice shelves, sending more icebergs into the sea, nudging sea levels upward. But for biologists, the bigger thrill is life itself. In conditions colder, darker, and more pressurized than most labs can replicate, life has not just survived, but adapted. These microbes may resemble early Earth organisms, ones that thrived before oxygen filled the atmosphere. Studying them is like cracking open a time machine. You can almost see the scientists in the heated lab tent, breath fogging as they crowd around microscopes, whispering in awe. For decades, skeptics insisted Antarctica's subglacial lakes would be sterile, poisoned by lack of sunlight and nutrients. But the samples from Whillans proved otherwise. The lakes are alive, and by extension Antarctica's under-ice plumbing is an ecosystem, not an empty void. The discovery changed the tone of the whole field. It wasn't just about whether life could exist down there. Now the question was how much life, how diverse, and what else is hiding beneath the ice. The answer wouldn't take long. Another drilling project, a few years later, would push the mystery even further. You brush frost off your hood as the scene shifts forward to early 2019, when another team of American scientists returned to West Antarctica. This time the target was Lake Mercer, a subglacial lake about 50 kilometers from Whillans, buried beneath roughly 1,200 meters of ice. On the surface the operation looked familiar: clusters of tents, generators chugging, hoses hissing, scientists wrapped in red parkas moving between stations. But Mercer was bigger, deeper, and less well understood than Whillans, and the stakes were higher. The project was called SALSA, Subglacial Antarctic Lakes Scientific Access. Their drill was a hot water system again, designed for clean access. Every drop of drilling water was melted snow, filtered to remove particles, zapped with UV light, and pushed under high pressure down a borehole that slowly snaked through more than a kilometer of ice. The goal: sample Mercer's water and sediments without contaminating them, just as Wizard had done with Whillans. It worked. After days of around-the-clock pumping, the borehole broke through into Lake Mercer. Cameras and sensors slid into the darkness, their cables spooling out endlessly, until they dangled in a place untouched for thousands of years. Pumps hauled up liters of lake water, while corers bit into the sediments at the bottom. When the samples arrived at the surface, excitement rippled through the camp. What they found startled even seasoned scientists. Microbial DNA was abundant. Mercer, like Whillans, was alive, but the sediments told an even stranger story. Tiny remains of diatoms, microscopic algae that usually live in the ocean, were found deep in the mud. That suggested Mercer, sealed now beneath ice, had once been connected to open seas, or perhaps even hosted open water during warmer periods in Antarctica's past. In other words, these lakes may not be eternally isolated. They may be part of a shifting, breathing system that ties the interior of the continent to the oceans beyond. The samples also contained ancient carbon, hinting that buried ecosystems may cycle nutrients across geologic timescales. Some of this carbon may have been locked away for tens of thousands of years before being re-released. For climate scientists, this raised a huge question: how much hidden carbon is trapped under Antarctica, and could melting or draining lakes release it into the global system, accelerating warming? It's like finding an invisible bank account of carbon dioxide and methane buried under the ice, one that might one day leak. The SALSA project also proved something else. These lakes aren't rare jewels, they're everywhere. If Whillans and Mercer both host microbial life, then odds are good that most subglacial lakes do too. That means hundreds of hidden ecosystems may be ticking away beneath Antarctica, each one carrying unique adaptations, each one a separate planet of biology. The scientists at Mercer worked long shifts in cramped labs, faces glowing in lamplight as they peered at slides, whispered over DNA sequences, and tried to process what they were holding. Every vial of water, every scoop of mud was a message from a world below, a place without sunlight, oxygen, or connection to the surface, and yet it thrived. Standing on the ice above Mercer in your imagination, you realize something profound. Antarctica isn't a barren desert after all. It's a layered, hidden landscape. Above, endless blizzards and silence. Below, rivers, lakes, sediments, an entire microbial civilization. The continent is less a block of ice, and more a cake with secret fillings. But if the lakes are alive and dynamic, then they aren't just curiosities, they're record keepers. The mud at their bottoms may preserve snapshots of ancient Antarctica, forests, warm seas, even times when the continent was green. Unlocking those records could change our understanding of Earth's past, and our predictions for its future. You draw your gloved hand across the frost on your goggles, and picture yourself staring at a core sample freshly lifted from the bottom of a subglacial lake. It's not glamorous, just a dull cylinder of mud, dark and damp, sealed in plastic. But to a geologist, it might as well be a treasure chest, because inside that mud are clues to Antarctica's past that no satellite, no radar, no surface expedition could ever reveal. Here's the idea: when lakes like Whillans or Mercer fill and drain, they leave behind sediments that settle in quiet layers on the lake floor. Each layer is a page in a diary, recording what was happening in Antarctica at that time. Volcanic ash may drift in, pollen may blow from distant lands during warmer periods, chemical traces of ocean water may seep through channels, or microorganisms may die and sink to the bottom. Over thousands and millions of years, these layers build up into a hidden archive. For paleoclimatologists, those sediments are pure gold. Antarctica has not always been an ice desert. 50 million years ago, palm trees and ferns grew here. Dinosaurs once roamed its warmer coastlines. Even in more recent times, just a few million years back, the continent's ice sheets retreated and advanced, like tides on a geologic scale. Every shift left a signature in the mud, different minerals, isotopes or fossils that act like timestamps. At Lake Mercer, scientists discovered diatoms, tiny silica shells from algae that normally live in the ocean. Their presence deep in the sediments hinted that at some point in the past, seawater surged into the lake basin. That meant the West Antarctic ice sheet must have thinned or collapsed, allowing the ocean to invade far inland. For climate scientists, this was like finding a crime scene photograph, proof that Antarctica's ice had failed before and could fail again in a warming world. Other cores tell different stories. Some reveal layers rich in organic carbon, suggesting times when ecosystems flourished. Others contain chemical fingerprints of shifts in oxygen or nitrogen cycles, hinting at how microbial life adapted over tens of thousands of years. Some even preserve ancient DNA fragments from organisms, long extinct, caught in the sediments like flies in amber. And then there's the physical structure of the lake beds themselves. Radar mapping shows deep basins, carved by glaciers millions of years ago, then filled with water and sealed. In some places, sediments may go back 10, 15, even 20 million years. If cores can be extracted cleanly, they could give us continuous climate records older than anything we've yet recovered from ice cores. Think of it as flipping further back in Earth's diary, to see what kind of world it was before ice ruled Antarctica. But drilling into these sediments isn't just about the past, it's also about the future. If scientists can understand how Antarctica's ice sheets responded to past warm periods, how fast they collapsed, how far the oceans reached, they can make better predictions about what rising greenhouse gases might do today. It's not just history for history's sake, it's a guidebook for survival. As you stand on the ice above one of these lakes, it feels strange to realize that some of the most important climate lessons for our future are buried not in tropical rainforests or coral reefs, but under kilometers of Antarctic ice. Down there in silent black lakes, the mud waits, holding answers written in silt and fossil shells, and unlocking them could mean the difference between understanding climate change and being blindsided by it. You steady yourself against the biting wind, but in your mind, the layers of ice beneath your boots start to shift, not physically but in the story they tell about our warming world. Because Antarctica's subglacial lakes aren't just hidden curiosities, they're active players in the unfolding drama of climate change. Here's the uncomfortable truth. The lakes and rivers beneath the ice don't just sit still, they influence how fast glaciers move, how ice sheets thin, and ultimately how much sea level rises worldwide. When a subglacial lake fills, it can lubricate the base of a glacier, letting it surge forward like a puck sliding across ice. When it drains, the motion slows again. This cycle of filling and flushing is like a heartbeat for the ice sheet, one that pulses faster as the world warms. In the past few decades, satellites have tracked surprising changes. Some lakes that were thought to be stable drained billions of gallons of water in just months, their surfaces collapsing while nearby ice streams sped up. Those surges of hidden water don't just vanish, they flow to the ocean beneath floating ice shelves, weakening their underbellies. And when an ice shelf thins, it loses its ability to act like a dam holding back the glaciers behind it. The result: faster ice flow into the sea, faster sea level rise. This isn't just theory. In West Antarctica, where Whillans and Mercer lie, the ice sheet is particularly vulnerable. Warm ocean currents are already nibbling at the edges of ice shelves. Add in hidden rivers flushing from subglacial lakes, and the stress compounds. Glaciologists warn that the West Antarctic ice sheet could be on track for a major retreat. If it collapses entirely, sea levels worldwide could rise by over 3 meters. That's not a few beach houses underwater, that's New York, London, Shanghai and Miami scrambling to stay dry. And then there's the carbon story. Remember those cores pulled from Mercer? They showed ancient organic matter sealed in sediments. If melting accelerates and subglacial systems release that carbon, it could amplify warming even more. Antarctica might not just be a victim of climate change, it could also become a contributor, unlocking greenhouse gases from its buried reservoirs. Of course, scientists are still cautious. The systems are complex, and the exact feedback loops aren't fully understood. But one thing is clear: ignoring Antarctica's plumbing is like ignoring the pipes in your house until water bursts through the ceiling. The hidden lakes and rivers aren't minor details, they're central to predicting Earth's future coastlines. Standing on the ice, you realize how strange it is that a place so far away, so empty, and so silent, could have such enormous influence on billions of lives. While cities argue about floodwalls and emissions, The real action is happening right here beneath your boots, in black water no human eye has ever seen directly. And if the lakes can drain, surge, and connect to the ocean, then they're not just part of climate history, they're part of the present and the future. Which leads naturally to the next question: where exactly does all that water go once it leaves the hidden lakes? You lean on your walking pole, squinting into the flat white horizon, but beneath your boots, water is already on the move. Subglacial lakes aren't isolated bowls, they're nodes in a sprawling network of hidden rivers that snake their way toward the coast, carrying meltwater from the heart of Antarctica to the sea. This underground hydrology was invisible until satellites gave us a way to see the surface breathe. Remember those strange bulges and dips in the ice, rising and falling over months? That was water filling and draining beneath, sloshing down invisible pathways. Some rivers are only a few kilometers long, connecting one lake to another. Others run for hundreds of kilometers, threading valleys carved into bedrock millions of years ago, still ferrying water today. Eventually, many of those flows reach the grounding line, the place where the ice sheet lifts off the bedrock and begins to float as an ice shelf. And here's where things get interesting. When fresh water gushes out under pressure, it doesn't just vanish into the ocean, it mixes with salty seawater, it stirs nutrients, it carves channels into the underside of the ice shelf. Sometimes it even creates buoyant plumes that rise and melt the ice from below. That process weakens ice shelves, the floating extensions of the ice sheet that buttress the glaciers behind them. Think of shelves as corks plugging the bottle, undercut them with warm water and hidden plumes, and the cork loosens. Once it's gone, glaciers flow faster, dumping more ice into the ocean, raising sea levels. But it's not all doom. Those hidden outflows may also deliver nutrients to Antarctic ecosystems. Where the subglacial rivers reach the Southern Ocean, they bring iron, phosphorus, and other minerals leached from bedrock. For plankton, that's liquid gold. In fact, these unseen rivers may help fertilize coastal waters, feeding the phytoplankton that sit at the base of Antarctic food webs. Tiny as they are, plankton support krill, whales, penguins, and seals, the entire biological circus that somehow thrives in the Southern Ocean. So under your feet, the same pulse of water that destabilizes ice shelves might also be fueling life offshore. It's a dual-role destroyer and sustainer, destabilizer and provider. The paradox is striking, and it's why oceanographers are now obsessed with tracing these subglacial outflows. They want to know where the water exits, how much it carries, and how it shapes the ocean beyond. Radar mapping has already revealed mega rivers under East Antarctica, some as long as the Thames or the Rhine. Models suggest these rivers could be draining enough water to influence not just local ecosystems but the circulation of the Southern Ocean itself, a circulation pattern that, by the way, helps regulate global climate. Standing in your insulated boots on what looks like lifeless ice, it's surreal to realize you're perched atop one of Earth's most important plumbing systems. Silent, invisible, and relentless, the water moves day and night, shaping glaciers, sculpting ice shelves, and even feeding plankton blooms in waters where humpback whales breach. The secret rivers remind you Antarctica isn't isolated from the rest of the planet. Its hidden veins of water connect directly to the ocean that laps on every shore, from Sydney to San Francisco. And to trace those hidden veins, scientists have had to build some of the strangest, most ingenious tools ever deployed in Earth's coldest desert. You exhale into the frozen air, and for a moment you imagine it curling into wires, antennas, and blinking consoles, because at this point the story shifts to the machines. Humans alone can't peel back 4 kilometers of ice, but with the right technology, they've started mapping, drilling, and even swimming through this hidden world. The first workhorse was ice-penetrating radar, slung beneath aircraft or mounted on sleds. It works like echolocation. Radar waves blast downward, pass through ice, and bounce back when they hit a boundary rock, water, or sediment. By the 1990s, those echoes were already revealing lakes like Vostok, and today, fleets of survey planes trace grid lines across Antarctica, turning blank maps into secret atlases of rivers and basins. Next came satellite altimetry. From orbit, satellites measure the height of the ice sheet with absurd precision down to a few centimeters. That's how scientists caught lakes filling and draining, their roofs bulging upward or sagging downward like giant invisible balloons. It was the first real proof that Antarctica's plumbing was active, not frozen in place. Then there's seismic surveying, the old-school boom and listen technique. Explosives or heavy thumpers send shock waves down through the ice, and geophones measure the echoes. The smoother and more mirror-like the reflection, the more likely it's water. It may not sound glamorous, but seismic work helped confirm the enormous scale of Vostok and other giants. But exploration means more than just mapping, it means touching. For that, engineers have built specialized drilling rigs. The Russians relied on mechanical drills, laced with kerosene, but newer projects prefer sterile hot water drills, essentially pressure washers, the size of semi-trucks. Snow is melted, sterilized and blasted downward to melt shafts wide enough to lower instruments. The boreholes don't last long, they refreeze within days, so the science has to be quick, precise and rehearsed like a spacewalk. And speaking of space, some of the tech is straight out of science fiction. Engineers are now developing autonomous submersibles, robotic torpedoes designed to slip through boreholes and swim beneath the ice. Some are tethered, some free-ranging, all equipped with cameras, sensors and samplers. One prototype called Icefin has already explored the underside of an Antarctic ice shelf, gliding through black water like a metallic fish, sending back footage of a hidden world. Future versions may dive into lakes themselves, tasting water and sediments directly. Cleanliness is an obsession. Every hose, every drill head, every probe is sterilized, baked, or zapped with UV light. Contamination isn't just bad science, it could destroy ecosystems that have been sealed for millions of years. So these tools are designed with planetary protection in mind. In fact, NASA pays close attention, because the lessons here double as training for Europa or Enceladus missions. If you can build a robot that drills through Antarctic ice without fouling the environment, you're halfway to designing one that can explore alien oceans. You picture the camp at Lake Mercer or Whillans, a noisy knot of generators and hoses on the surface, a glowing warm tent filled with laptops, and 1,000 meters below, instruments dangling into pitch-dark water. It looks crude, almost improvised, but in reality it's cutting-edge technology, the best humanity has to offer for probing one of Earth's last frontiers. And yet for all the radar sweeps, boreholes and robotic probes, most of Antarctica's hidden lakes remain untouched. Hundreds are still nothing but squiggles on a radar trace, waiting for someone brave or foolish enough to drill down, which means the real adventure is still ahead. You stamp your boots into the snowpack, listening to the crunch, and imagine the conversations happening right now in planning rooms far from the ice. Because if Antarctica has already revealed a few secrets through Whillans and Mercer, there are still hundreds of lakes no one has touched. The future is about going deeper, going cleaner, and going bolder. Take Lake Vostok. Even though the Russians pierced it in 2012, the methods were clunky, kerosene-filled boreholes that left doubts about contamination. Future missions are already being designed to do it again, this time with sterile hot water drills and robotic probes that can swim directly into the lake. The hope is to send down an autonomous submersible small enough to slip through a narrow borehole but advanced enough to map, film and sample the lake environment. Think of it as a mechanical fish, exploring waters, sealed for 15 million years. Then there's Lake Ellsworth, in West Antarctica. The British tried and failed to reach it in 2012, but they haven't given up. Plans for another attempt involve redesigned drill systems, improved borehole stabilizers, and even modular submersibles. Ellsworth is especially tantalizing because its sediments may hold continuous records of climate stretching back hundreds of thousands of years. It's like a library of Earth's past, sitting there under ice, waiting for someone to finally unlock the door. And beyond those marquee names, the network of smaller lakes beckons. Hundreds of them, mapped by radar but untouched. Some are thought to connect into rivers that run all the way to the sea. Others may be so isolated that their microbial life has evolved in complete genetic solitude. Scientists dream of sampling 10, 20, 50 lakes to compare ecosystems, to build a kind of biodiversity atlas of Antarctica's underworld, but each one requires immense logistics, airlifts, drilling rigs, power stations, weeks of round-the-clock work in deadly conditions. International cooperation is also on the table. The Antarctic Treaty already requires strict environmental protocols, but big projects increasingly look multinational. NASA teams sit alongside British Antarctic survey planners, who in turn coordinate with Russian, French, and Australian scientists. The rationale is simple: these lakes are too valuable to risk spoiling, and too expensive to tackle alone. So the future may look like joint missions, shared equipment and global stewardship. And of course the shadow of astrobiology looms over everything. Europa Clipper and future missions to Enceladus are built on lessons learned here. Every time a clean borehole is drilled, every time a probe is sterilized, it doubles as practice for exploring alien oceans. When you watch video of a robot sliding through a subglacial borehole, you're basically watching a dress rehearsal for drilling through Europa's crust one day. But even with all this ambition, the truth is humbling. Out of more than 400 known lakes, only a handful have been sampled, and even those briefly, the vast majority remain nothing more than faint reflections on radar screens. They are Earth's last great blank spaces, undiscovered, untouched, waiting. Standing in your parka on the Antarctic plateau, you can almost hear them, silent, patient, dark pools beneath your feet. They've waited millions of years, they can wait a little longer, but the future is clear. Humans are coming, and with cleaner drills, smarter robots and bigger questions. And when those questions are finally answered, they'll lead us to the biggest one of all. Why do these lakes matter so much in the grand story of our planet? You stamp your feet to keep warm, staring out over the endless ice, and realize we've reached the heart of the question. Why do these hidden lakes matter? Why should anyone care about a few pools of water buried under kilometers of frozen crust? First, they matter because they rewrite how we see Antarctica itself. For centuries, people imagined it as a dead block of ice, lifeless and still. The discovery of hundreds of lakes, rivers and microbial ecosystems shattered that illusion. Antarctica isn't a frozen tomb, it's dynamic, restless and alive, even in its deepest darkness. Second, they matter because they hold climate records more complete than anything we've seen. Sediments at their bottoms preserve chapters of Earth's history we can't find anywhere else. They tell us when Antarctica was green, when seas surged inland, and how fast ice sheets collapsed in past warm periods. Those lessons aren't abstract, they're the best guides you have for predicting what rising carbon dioxide means for the future of Miami, Mumbai and Melbourne. Third, they matter because they're ecosystems sealed in time. The microbes in Whillans, Mercer and probably dozens of other lakes show us how life can adapt without sunlight, oxygen or contact with the outside world. Each new DNA sequence broadens the story of evolution, proving life doesn't just endure, it thrives in ways we barely imagined. And the potential for undiscovered species is enormous. Every untouched lake is a vault of biodiversity, waiting to be opened with care. Finally, they matter because they push us to think beyond Earth. Every borehole drilled here is a rehearsal for Europa, Enceladus, or any icy world with a buried ocean. If microbes can survive in Vostok or Mercer, then why not under Jupiter's moons? Antarctica forces us to confront the possibility that life in the universe might be common, and that Earth's hidden waters are just one example among many. So why do they matter? Because they link everything together. They connect Earth's deep past to its precarious future. They connect geology to biology, microbes to galaxies, Antarctica to outer space. They remind us that even the most silent places on Earth are teeming with secrets, and that those secrets may hold answers to questions we've been asking since we first looked up at the stars. Standing here, boots planted on ice, older than human civilization, you understand, the last unknown lakes aren't just about Antarctica, they're about us, our past, our future, our place in the cosmos. And they're about the humbling reminder that no matter how much we think we've mapped the planet, Earth still keeps some of her greatest wonders hidden out of sight. So now, as the story slows, let the harsh winds soften in your imagination. Picture the endless white plains, stretching away under a twilight sky, the ice glowing blue in the low light, and the sound of the world fading into silence. Beneath those plains, in the dark and